All right, this is the implementation of the direct analysis method using STAAD. Um, when we open up STAAD, what we have in terms of the graphical user face is on the left-hand side. You have a selection of options. It's essentially a menu over here at the top. This is the name of the edition of STAAD that you're using. And then there's like a preview window, and of course your open window. Everything is pretty standard. So when you want to create a new model, obviously you just go to new, give your model a name, and I am going to actually browse to my desktop, see where these things are kept right now. That's a good enough location. Cancel out of that, and just say, give it a name. You can set here which type of model that you're building. This is all new to STAAD.Pro. So there's the analytical, there's the physical, and there's a building model. Here we're creating a building model. Here is where you set the units, and with that, you can create the model by selecting create. So immediately, the program launches, and of course you're faced with, you're given the basic graphical user interface. On the top, we have, at the very top, we have icons, which are familiar icons. No need to explain what those are. The name of the file that you're working with will always be there at the top, the save name of the file. The basics of the ribbons, obviously it's the more recent format. So the file will take you to the options involving file. I'm not going to go over everything right now in depth. Just giving you a feel for the graphical user interface. Geometry is where the modeling takes place, physical creation of the modeling, that's obviously geometry. View tab is for different view settings, selection. Everything is self-explanatory, but it allows you to select different parts of the structure as you create it. Specification, this is related to the releases or any type of other property related to the model. We'll find out more about it as we actually use it. Loading tab, I'm not going to click on that yet. Analysis and design tab is where you set your parameters of what load cases will be analyzed and designed. And the utilities tab is where you can access the command file, among other things. And there are other utilities in here that can help you in the process of creating a model. So going back to here in the utilities tab also, I believe we can set the units. So we always want to be able to get to where we can set the units of the file. I don't see the option right now, but the units, the current units are displayed on the bottom as kept feet. Let's go back to the geometry tab. Okay, apologies. In the geometry tab is where you can set the units, and this is your input unit icon under the structure section. You can change it to whatever unit that you desire. So if you want to use right now the length, it was currently set to kip feet, so we can select inch, pound, and the one that is shaded is the one that is the current selection. So you hit apply and you see pound inch down at the bottom. I'm going to set it to, in this case, KSI and apply, and just leave it at that right now. The reason why I'm doing that is because I want to take a quick look at the material properties on the structure and kind of get a feel for, the values that are set as default under material. Okay, so I don't see the database for it just yet, but we'll start some modeling, and then we'll see where this thing is residing these days under STAAD. This is a newer version of STAAD, so they kind of move things around a little bit, but nonetheless, we'll be able to figure out where everything lives once we start building the model. All right. So I'm going to set up a frame that's based on learning module number 9 from MASTAN. It's a simple structure, and in terms of its configuration, I'll use that. I don't know the exact properties right now. I don't have everything in front of me. However, this is just a quick video to demonstrate how to build the model and load the model and have all the settings that you need, and also to demonstrate how to implement the direct analysis method. All right, so on the right hand side, again, going through the graphical user interface, on the right hand side is the database kind of layout that STAAD has that tells you the, in this case, the analytical or the numerical values of certain items. So what we want to create, here's the material tab. So when we want to create a new node, we would do that in this box right here, or you can do it graphically. I like to use the database because I have better control. This also tells me, in terms of my workflow, on the left hand side, you'll see the phase of the workflow that I am in. I am currently in analytical modeling, and in the middle is the graphic, the screen, the graphical display of where your model will be placed. Here on the bottom left, we have the default coordinate system. You can see Y in this case is vertical, up and down, and X and Z are on the horizontal planes. All right, so I'm in analytical modeling, and also these are the different phases, if you will, the different selections that can send you into different areas, change your database that would display on the right hand side, and it's applicable to the modeling step that you're at. All right, so we're at geometry, so let's just define the structure. And as a matter of fact, I did say that I'm going to use inch pound, I'm going to use kip feet instead, because I like to define my structure in feet unless noted otherwise. But I put my materials in KSI. It's a long story. So 0, 0, let's start off with that. Let's say the structure is 12 feet high. So the next node will be 0, 12, and we'll say it's 20 feet long. So we'll have 20 feet, 12, and then the last node would be at 20 and 0. There you have it. Then you can take the view, select views, and we can select the XY plane. Take a view of the structure, zoom out by scrolling the mouse, the wheel of the mouse. Let's go back to geometry and we'll start defining some elements, some beams, columns. Right. So add beam by selecting the add beam option and just connect the dots. I like to add kind of my columns together so I can compare them in terms of numbers. So now I've modeled the stick element of the beams and the columns. Right now you don't see anything but dots and lines. We'll expand on that in a little bit. So the other thing, just in terms of the basic model, let's just go ahead and put in the supports. Now you notice when I click on supports for this screen, the nodes went away. In order to view the nodes again, you right click anywhere on the screen in the graphic display area and select structure diagrams, and we'll come over here to labels and say nodes, and I'll go ahead and turn on the numbers and hit apply, and they pop back in. Here on the right hand side is where you can create or define your support condition, and we have defaults, so you can just select create, and this dialog box up here that says create support, here you'll just select from the pin tab, add it, highlight, make sure that the assignment method is on use cursor to assign, and then click the assign button, and you can then just click on the node that you want to support at. Now, because this is a 2D frame, and STAAD is a three-dimensional analysis and design program, we have to brace this frame out of plane. So I'm going to, I only want to run a 3D analysis, but we'll get an error if we don't brace it out of plane, because the computer is going to say that the structure is unstable. And indeed it would be like this. So I will create another type of support here. This support is more specific. This shows that you can get in there and control what you want to control regarding the support. We'll release any action in the X, any axial action or displacement in the Y. We'll keep the C locked so it doesn't move in and out of the XY plane. We will go ahead and release all of the moments just as well. And this structure is stable under that configuration. So we'll go ahead and add that support. You see STAAD pops in the question mark. That just indicates that it's a unique support, user specified, not something that is out of the box. Again, I use assign, and I will assign that type of support at both locations. You have a graphical representation of the support and which displacement criteria is locked in. So here we have braces, if you will, out of plane. Going back, let's go ahead and give this thing some properties. And I am going to cheat for a second because I want to go ahead and model in the exact same thing as I did before. I'll pull up the file, another SAP file of what was done before. because I don't have the memory properties in front of my head, in front of my face, and I don't know it off the top of my head. I think they're W12s or something like that. At any rate, it doesn't matter. Let's just pull up what the learning module is based on. There we go. We have W12 by 58s for columns and W24 by 76 for beams. All right. That being the case, let's come back over here and we want to select properties, and now we have to load in those sections into our model. Go to the section database, and we select our W12 by 58, I believe it was. Let's see. And add it. You can see the material that's being selected along with the element when you bring it in. And then the other one was W24 by 76, was it? Yes. W1224 by 76. And come up here to the 24 series. Select that. Go ahead and add it. It's okay. Let's go ahead and save the file. Now we'll assign these properties, these member sections, to individual elements by the same method as we did for the supports and the nodes. Come over here and select that. It's applied. You see R2 being displayed. That's just a reference material, and that's the name that it's been given. It's a reference material, R2. This one right here will show up as R. Look, now this should be R1. So let's switch it up. And this 24 should be R2. There we go. Make sure in terms of what actually is assigned, you can display that again by going back to labels, and you can select the properties of the sections as well as the beam numbers and hit apply, or the element numbers in this case, not column beams. This is beams and columns, but this is a beam element. There we have those that configuration. Now I don't know, what's the default orientation just by looking at it, and so I actually need to view that to see how the structure is oriented. Are the columns laid out on the weak axis or the strong axis? Same thing with the beam. It's not the case. We're not sure. So we can display this in different ways. We can set up the model to be extruded. One of the quick and easy ways of doing it, again, is by right-clicking, going over to our structures diagram, and hit. We could do full 3D, or we could just do the outline, section outline, hit apply. You see the outline of the structure, gives you an idea of what we're talking about. You can see that the structure, the column is oriented such that the web is parallel to the X and Y axis. Here we're going to turn it around because we want to make this structure a little weaker in terms of its analysis. In terms of we're gonna weaken it during the analysis, and we'll get the most dramatic effects when these things bend about the weak axis. And that's the way it's set up in Learning Module number 9. So to rotate this cross section, we need to go to the beta angle section of our properties tab and create a beta angle, or edit or delete. So we create a beta angle, and here we're just going to type in, this is weird, angle, but type in 90 degrees. So it's okay. Come in here and use the cursor to assign, and once we click on it, you can see that our columns are rotated 90 degrees. Now they will be bending about the weak axis for any action that occurs in the X and Y plane. Again, save the file. We're almost done here in terms of our model. We actually are done in terms of the structure. And let's go ahead and set our units. I like to go back real quick to inch pound. I'm sorry, inch KSI units, basically inch kips. So hit apply, because when I go into the loading section of the analysis and I set my direct analysis commands, if you will, for the structure, I like to use kip KSI and not kip per square foot. Excuse me. But that has a weird way of switching it back. I'm just going to demonstrate it to myself to make sure that it's not me, it's the program. All right, the unit says kip inches, and when you define direct analysis, this is where you put the definition in for it. Under the loads and definition cases, expand definitions, and you would select direct analysis definition, add it, and then have all these parameters. Now, the flex parameter says essentially if you will reduce the flexural stiffness of the element, yes, 0 is off, 1 is on. So we added the yield parameter. Now this is an actual value. So like I said, my units are 50 KSI. I'm sorry, RN skips or inches, so I want to put in 50 KSI in my mind. That makes sense. So I add that. Okay. Come back over here on the axial parameter. No data is required. That just means that once we add it and apply it, it applies. And if you were to use notional loads in your analysis, this would be where you would specify the load factor for the notional load. We're not going to do that here. We're just going to add a value, a lateral load to it based on the instructions of learning module number 9. We'll say, okay, come over here, let's expand this and see what we have. Now, I clicked on 50 2 times, so I'll go ahead and delete one of them in terms of the yield stress. Now I'll take my flexural parameter and I'm going to assign it to the view. I'll assign to all. Yes, I want to proceed. Also want to make everything 50 KSI. Assign to view. Axial. And I will assign to view. This reduces the axial stiffness of the element, flexural stiffness of the element, and this is the yield stress that we use to define so that we can figure out what our eventual tau sub b value would be. Now, I'm going to go back to geometry for a second. Save the file. And I didn't talk about the ability to release the connections, the ends of the members. But if you were to do that, although we don't need to do that for this module, just to kind of demonstrate the section where that would apply, it would be under the specification sections, and we would come in here under specifications, and these all apply to beam elements, if you will. That's why it says beams. And you can release moments or axial forces, not necessarily axial moments, or you can release forces. And the axial to shear, or shear in the vertical, shear in the horizontal, etc. You could also come in here and specify partial moment release and other things of that nature. Or if this was a truss element and you wanted to just make sure that it behaves only as a truss, you can come here and specify that type of property for the element. Here we're not going to do anything, but this would be the area where we would do that. So close the file, save it. All right. Let's go back to geometry. Let's change our units. Now I'm going to change to, not going to change anything, because just remember I don't have to put in a distributed load or anything like that. So since I don't have to do anything special other than put in axial loads, I can use the force unit of kips. All right. I like to put in my distributed load as pounds per foot or kips per foot, or just basically on a per foot basis, and my axial loads on a kip value. It's pretty standard throughout all of our textbooks. So going back to my loading section, here is where we would define the load cases. That's the name that STAAD uses, which is different than what SAP use or ETABS use. Load cases in this case are just basically your basic load cases. Vertical load, it could be dead load, live load, etc. Here I will be defining a vertical and a horizontal load. So I'm going to come in here and I'll just call this vertical. And this is just a name. It's also a type. So if, like I said, if I want to come here and use our specified load type so that it can be combined according to the building code load combinations, this is where I would do it. But I don't want to do anything special. This is just a demonstration. I say none. Vertical in there. Spell it out. Add it. I'm going to do the same thing for horizontal. This is just a simple load. This is where I will put my horizontal loads in. That's that. Add. Close it. I'll come over here. Under, now you select that load case that you've created. And this is where you actually get into defining the load value and type itself, vertical, concentrated, whatever you want to do. So here I'll put a nodal load. It's in the Y direction. I have to cheat. I have to go back to this other program so I can see what the load is. I believe it's 130. So I'm going to come into loading and expand this from my QSub view. Here, 130. 130 is the ultimate load in this case, so I'll put in minus 130. Add the load. It appears under that selection, again using like this explorer, this tree setup, and you select the load. Again, use cursor to assign, hit assign, and then select the nodes that you want to apply it to. Now you can see they're off the screen. So how do you know you're doing the right thing? Again, you come back over here and you can display it. You can zoom out. See, as much as I zoom out, these loads are getting bigger and bigger, right? That's because STAAD displays it as a scale view. I can right click, come over here to structure diagrams and scale it down a little bit. So for my point force, I can, let's see if I scale down, see what happens. It gets bigger. Let's go ahead up. Apply results immediately, then we'll find out. There you go. So scale down a little bit. Point force, we'll say apply. Okay. Oh, also you can display the value of the loads here. Labels, load values under the loading display options. And okay. And it shows you what loads you place on the structure. All right, same thing for horizontal. Notice when I click on horizontal, the verticals went away. I click on the vertical, they come back. We're going to define a load that in this case is, I believe, we're going to use a load value of 0.3%, I think. 10% is the default. We're going to add a different load value because I am not modeling this. I am not modeling my structure out of the plane. I'll come back over here and cheat a little bit. Take a look at my load value. And here we're going to use a value of 13.78 kip. So I'm not modeling the structure in this displaced condition, if you will, the tolerance that's allowed but via erection. So I'm not modeling the erection imperfections. I'm just going to add additional vertical lateral load in order to capture that. So come back over here, 13.78. Let's define that nodal load in the horizontal. We're under that. It's a lateral load, positive x direction, 13.78. Let's get out of here. All right, 13.78. Hit apply, add. There we go. Use cursor to assign it. Voila. Hit escape. Save the file. Now, in order for STAAD to do its analysis correctly for vertical and lateral loads, the direct analysis requires the second order analysis requires that those nodes are analyzed together and not individually and summed up as superimposition, because of course, as we know, that does not apply for the direct analysis method. All right, so we have to come in here and define a special load case in order to analyze the effects of the vertical and lateral load together. Now that load case is a repeat load case. And we may need to go to our model over here again to do a little investigation. Yep, just to be sure. So we have a repeat load case. All right, so come over here. Oops. And we go to definitions. I'm sorry, we go to the old case. Okay, so add. So define load generation primary. Let's type that repeat for a second here. Let's see what happens. Add it. And we could have called it vertical plus lateral or whatever. I'll switch the name back over. Now add under that definition, repeat load. So I have to select repeat load here, and it shows me the available cases. I'm going to slap both of them over there. No factor for those basic loads because I'm using LRFD, and I put in the loads as ultimate loads. So I'll just go ahead and assign that, add it, close it, come over here. Let's edit the name of that. I'll just call it vert plus lateral. Vert plus horizontal rather. Alright, so change it, close it. Now, if I want to see what's going on with that, you can see the loads display together under that load combination. Hit save, and that does it for the loading. Now, we need to go in here into our analysis and design section and set up some parameters so that we can analyze the structure. Let's see here. We'll come in here and define the command. We would say that we want to perform a direct analysis, and we want to use LRFD as our option. We'll print all. We'll go ahead and do 20 iterations. We could talk about this in another video, but this is the number of iterations we'll go through, which is basically a second order analysis, and it's the maximum iteration that it would allow before it basically says that the structure is unstable or it's not working. So it will not go past 20 iterations. You can also specify tolerances for tau or displacement. We'll talk about that in another video. So we'll add this one after current, close it, save the file again. Let's come in here and the next step is to go ahead and do a little bit code design. In order to do that, again, I'm going to cheat. I'm going to go to my model that's already prepared, go to my design section, take a look at the parameters that I've just defined. All right, pretty straightforward stuff where we have our code that's defined. We have yield stress. We have a ultimate strength, a tensile value, ultimate tension strength. We're tracking the beam. We have a certain amount of detail check those elements. I will go ahead and define the same thing in my other model. I will define parameters. Come over here. Let me close this. Let's change our code. And I want to use AISC 36010. We can do commands. That's afterwards, but define parameters is what we start off with. And as I said, we would go ahead and put in our design method. We have it as LRFD. Add that. So we'll follow that up with our yield stress, even though it doesn't have to be in this order. We'll just do it like this, the way it was presented. Add our F sub U value, which is the ultimate tensile strength of the steel. Here we'll put that on the 65. That's applicable to 8992 steel. Put that in. Let's see if we can, and then we'll go ahead and put in a beam value. This is, the locations where a design check would occur. Every 12th section, very detailed. Every 12th section along the length of the member, we'll do a design check. And finally, we would select our tracking. We'll put it out to the maximum detail. We'll add that, close it. We would just assign, assign all this to view because we want to do everything. We want to we want it to apply to everything. We want to do everything at once. That's the quickest way. If it applies to everything. There we have it. They're all assigned. Close that. Let's bring in the command. Let's go ahead and do a code check. This tells it to actually check the numbers based on the code. Add it. It's weird, but it's the way that SAP does its analysis and design. Now assign it to the view. Okay. And that's that. We save the file. Now we're ready to run the analysis. Now we can get an error, and I'm going to tell you where this error is going to come from. It's probably going to come from the 50 KSI when we use the direct analysis method, and it, for some reason, just in the structure of the command file, it wants to be a different value, 72. It wants to be in kip feet. So this is where we could get an error. So let's see what happens. Run the analysis. No error warning. Oh, that's good news. So let's check our. Tells you it's an error. Didn't even say. Now it says the yield stress is out of the FY values out of the normal range on line 51. Okay, so where's line 51, right? You go to line 51, as I said, that's your direct analysis method value. So now let's go back in, and you can see from your utilities, if you go into the command file, the way that this thing is set up, when you read the command file, it starts with units is kip feet, and nowhere here is the unit change before the direct analysis command is placed in it here, and this is where you define direct analysis. So let's just go ahead and make that 7200, which is kips per square foot. Okay. And then we save it, close it. We updated our command file. It's going to read it. It's liking it. Now, let's go ahead and display this thing in overview. Run the analysis again. So it's not good. Now we have multiple errors. All right. Margin civil elasticity. All right, this thing is kind of flipping out. So let's come over here and see what needs to be done in terms of our model. We'll go to let's go back to our loading tab. And we know the margin civil elasticity has been defined. And this is the glory of STAAD, and this is why I don't like using STAAD. All right, so now it's asking me for the material. So for some reason, I lost the material. Let's go ahead and edit this thing right here. Or cancel. Let's assign material. So we'll go to the material section. It doesn't know material. It's like, what the hell are you? Okay, so we'll assign steel to everything here. Okay, there you go. Now it's happy, presumably. And it's good that we see these issues that can pop up when you're creating a model and you think you've done everything correctly because you followed all of the correct procedures for the input, and yet you still have these little bugs that need to be corrected. Let's come over here, and we're not going to cross our fingers because we know we're right now. And there we go. We have no errors, no warnings, and it gives us 3 notes. We'll check out what our analysis output is telling us here, and the notes are regarding the procedure of implementing P delta or direct analysis and something within STAAD in terms of the moments and the balance of the moment. This does not affect your results. We'll come immediately to still design area, double click on it, and we'll see whether or not these elements have been analyzed, and they have been, and we see some values that tell me that these things are failing, and I'm seeing some outrageous values in the beginning. So I'm not sure if yeah, no. All right, it's set up correctly. The way that it's okay. All right, gotcha. So this is just an output that tells you the member. It's not aligned correctly. So here's the member one. Here's the section table results slash FX, critical condition slash MY. It gives you the moment value, the ratio value here, etc. So this is where you would get the kind of like the calculations, the detailed analysis of those members in terms of what happened in the still design section. This would just be the text output, not the visual output. Let's go ahead and close that, and we go into our post-processing phase. We want to see the results for what's on the right hand was already selected. I should shot it over to the left, but I only want to select what's applies to our vertical and our horizontal condition. Hit apply. Okay. Come over here and we can take a look, and we get results of displacements of nodes under that condition under this load case. We want to take a look at our beam results. So here we have our beam results, and it gives you maximum axial forces, bending moments, shears, etc. There are cookie cutter layouts where you can figure out kind of like what's going on in terms of the utilization or the code, the beam stress, and displacement reactions. These are all just default views and setups. So here we have the results that shows you which members are stressed, what's in red is overstressed, and what the values are. You can see it's listed as member 2. It gives you the section, it gives you the actual utilization ratio, the demand capacity ratio. You see those 2 columns are stressed out, and that in short is the direct analysis method that's been implemented. Now we could always come back over here and figure out what size works for these elements, but the objective of this particular video is to show you how to implement the direct analysis method using STAAD, and that's what we've done. It's a wrap.